Okay, now let's take a look at triple integrals. If you had fun with double integrals, you're going to love triple integrals. So let's see what we have here. Now remember, we did use double integrals to find volume, but the double integral of just your area of region of integration actually finds the area of that region of integration. And same sort of premise here. Anytime you are evaluating the triple integral of a volume region, you're coming up with the volume of that particular region. Like say in this picture, if you set it up, as you'll see how we set these up. Now rectangular coordinates, we had either the possibility of dy dx or dz dy dx or dx dy. Now we have the possibility of 6 orders of integration. And I won't read all these out. You can read these. dz dy dx is often very commonly used. So is dz dx dy. I never asked to do 6 orders. And there are some problems that would be extremely difficult to come up with all 6 orders without seeing the region. But some are not that bad. And okay, let's take a look at what we got going on here. Now, remember that double integrals, if let's say you're going dy dx, that means if you go first with respect to y, that means the only variable you can have is the variable that's remaining, x. And the same kind of premise is here. They're only setting this up for dz dy dx, but the general idea would apply to all orders of integration. In this order, now this is assuming if you're integrating a function, so theoretically there's times we're going to be finding volumes of a volume, regions, that sort of thing. But like I said, that definition above, if that function right there is not there, you're just finding the volume of the region. Well, notice it starts at dz first. That means the variables for your triple integral on the farthest inside limits can be numerical or any combination of x's and y's. You can only integrate with respect to the remaining variables. So let's say you move to dy, and let's look here in the middle. So notice that has an h1 of x and h2 of x, meaning it can only be with respect to x. And then just like before with double integrals, the outside limits must be numerical. So like for example, let's say if dy was first here, that means this first integral can only have x's and z's in it. All right, let's take a look. Now this is just kind of, obviously as you've seen from double integrals, the setting it up is quite the challenge. The mechanics aren't too bad. I don't usually make the integrals too difficult. So, but let's kind of walk through this one here and see what we got going on. Now this triple integral, so it's already kind of given to you. It's just a matter of working this out. So you see it as dy first. So you can essentially ignore the ln of z right now until the next integration where z becomes the variable. So the antiderivative of dy would just be y. We go from 0 to 1 over x. So we plug in, which basically makes it 1 over x times z, which I just have x over z here in the bottom. Now, you can leave the 1 over x here. You don't have to do it the way I did it here, but what I did, it is correct. I talked about this with double integrals. One of the things you learn in Cal 1 is, never pull out your variable of integration, which is true. But you see, technically, it's okay to put this 1 over x between these two integrals because the 1 over x doesn't become a variable until you get to dx. Now, it would be wrong to take it all the way outside. But I could have just left it, but I just did that for show to show you that this is okay to move that right there temporarily between those two integrals. Because we're only focusing on z right now. Now this might look like it would be integration by parts, but it is not. It's just u substitution. If you let u equal natural log of z, your du would be 1 over z dz. And u of e2, so ln of e of the 2, ln and e, remember, are inverse functions, so they essentially cancel each other out. So ln of e squared would just be 2, and ln of 1 is always 0. Another way to think of it is 1 is the same thing as e to the 0, so it would leave 0. So now you just have u du going from 0 to 2, and we're through with the ln. We don't have to go back to our original variable. That's why I like changing the limits of integration. So we have 1/2 u squared, put in 2, put in 0. That's going to make it 1/2 times 4, and that's where this 2 is coming from right here. Then we have 1 over x dx. So the antiderivative of 1 over x is natural log of x. 4 and 1. So you put in 4, you put in 1, that actually cancels that term out because ln of 1 is 0. And you have 2 times ln of 4, which is perfectly fine. That's also mathematically equivalent to if you lifted that 2 up and made it 4 squared, natural log of 16. So 2 ln of 4 would be the exact same thing as natural log of 16. Okay, so here's another one where it's just working out the mechanics. And first one, dz, so we have a sine of y, so we can ignore the sine of y. This time I didn't move it between the two integrals, even though I could have. But the antiderivative of dz will be z from 0 to 1 over y, so that just brings in a 1 over y. And because the y is not till the last variable anyway, so now I have a sine of y divided by y, but notice the next integral is dx. So the antiderivative of dx is just x, and that brings in a y over 2 minus 0, which just brings in a y over 2. And that works out real conveniently because that'll cancel that y. And so now you just have 1/2 the integral of sine of y from 0 to pi over 2. Antiderivative of sine of y would be negative cos of y. And I could have reversed the limits of integration. I normally do that. You've seen me do that before if you've watched the other videos. This time I just left it. So it's negative 1/2 cosine of pi over 2 is 0, cosine of 0 is 1, and you end up with positive 1/2. And I did this one in Maple just for the heck of it, and Maple also says it's 1/2, so I like my chances of being correct. Now this is an interesting problem. This is a reordering of a problem. This is certainly something that I'd like to consider putting on a test, because this is one where actually any of the 6 orders aren't too confusing in this, and you don't really have to have the graph even to do this, but this is a very simple graph as far as if you're ever going to have anything in 3 dimensions that you would call simple, this would be it. So what I like to do to reverse the order of this is, since we know that this is dz, so z is being represented by, we're bounded by the xy plane with a 0, but then now that's what z equals right here. So once you have the z equals, you can rebuild this into like a normal looking equation of the plane. So I multiplied both sides by 3 to get rid of that 1/3. And let's see, and then I just moved everything around and solved it to get it in this form right here, where sort of a standard looking equation of the plane, or maybe that's the general equation of the plane, but either way, don't worry about the terminology there. So x plus 2y plus 3z equals 6. And this graph is actually called a tetrahedron, I believe is a term for it. It's you see it's a plane, it's a graph of a plane, but it's bounded in the first octant, so it forms that kind of 3-dimensional triangular looking shape right here. Now why I said this was easy to graph is because it's going to be it's a plane, so it's going to have straight lines connecting between each portion, and you can get each of the intercepts real easily. So in other words, to get the x-intercept, you zero out y and z, and that puts it on 6. To get the y-intercept, you zero out x and z, which gives you 2y equals 6, which is 3. And then for the z-intercept, 3z equals 6 and x equals 2. Now, but you didn't have to graph that, but like I was saying, it's if you were going to graph one by hand in 3 dimensions, that's a pretty pleasant one to graph because it's easy. Just going to bring that down a little bit so see it a little bit better. Now, here's how you want to think about this. So that we asked for the order up here. I believe it says dy, dx, dz right there. So obviously, just see you have to be given whatever the new order is. And we're still, everything lower limits in this one are all bounded by 0. We're in the first octant. So no matter what order we're in for this problem, they're all zeros on the bottom. Now it's just figuring out what the uppers are going to be. So if we're looking for y now in terms of the other variables. So all we do is take our equation, and well, actually I'm jumping ahead to the next step here, but anyway, what we would have done originally is take this equation, I'll scroll back up here and show you right here, solve that for y in terms of the other variables, because technically, you know, that if dy is first, that means we can have x's and z's, so there's what it would be, 0 to that one. Now, the thought process now is when you move over, now we're only in the xz plane. We've essentially used the y, so we're through with it, and if we're in the xz plane, that means y is 0. So you can take this equation and replace y with 0, and that's going to give me x plus 3z equals 6. Now, to know what I want to solve for is what is my, because you know it depends on which comes first here, dx or dz. That means dx is first. So if I have x plus 3z equals 6, I need to be solving for x in terms of z. Not the other way around would be z in terms of x. So x in terms of z would be x equals 6 minus 3z right there. Now the outer limits must be numerical. Our outer limits are dz, so all you're doing here is just using the z-intercept. So 3z equals 6. That means our last one's numerical. It's going from 0 to 2. So that integral, yeah, this actually relates, if you just did a double integral of this original function right here, you know, that would kind of be the same thing as the triple integral of just dy, you know, so yeah, it would be like if we would have said, you know, z equals, this we would have done z equals that function. But see, if you think about it, if you integrate dz, that gives you a z, and it drops this down in there, so that would have been like starting out with a double integral. So it would have accomplished the same thing. So the working out the triple integral is finding the volume of that tetrahedron, which I'm not likely to really ask you, because I'm going to see if I thought I put this in the notes, unless I put it back in the notes in that other section, but well, anyway, I'll just tell you, because it's, in a way, it's kind of pointless, because what happens is the volume of a tetrahedron, instead of making you go through all this triple integral business, really is just the area of the base triangle times the height of that solid. So if you can see that the area of that base, that's 6, x is 6, y is 3, and or maybe it's a third of that. Well, no, not that. Well, a half. So half of the area of the triangle is definitely a half. So it would be 9, and that's what it is. 9, and then times the height, but then it's 1/3. So it's 1/3 times the area of the base times the height. So the area of the base is 9. 1/3 times 9 would be 3. 3 times 2 is 6. So this is definitely what the area of that region is. There, excuse me, volume of that region in 3 dimensions is 6. So there's a good chance that my integral is set up correctly. I didn't put that one in Maple. I guess I didn't bother to do that, but you could check if you want to. But I wouldn't worry about it. I'm pretty sure the original one's going to equal 6 also. So, all right. Oh, and I chose another order. You see it came out to be 6, but same idea. So if you went dx, dz, dy, you're starting with that same plane equation. You would solve for x in terms of the other two if it's on the inside. So there's 6 minus 2y minus 3z. And then once x is done, you let x be 0, and you solve for z, the middle one, in terms of the outer one, y. So solving z in terms of y. So if x is gone, you have 2y plus 3z equals 6. So z would equal 1/3 times 6 minus 2y. And the outer limits is y. So 2y equals 6 means its intercept's 3. So it's going from 0 to 3. Now this one I'm asking to switch it, but then we'll evaluate the original integral and see what happens. Now I've only graphed the area base there, dy dx, just because that's why, you know, anything I wanted to, if I had you to have to do some really rearranging, except for the tetrahedron, which is easy, but something like this I would have to show you a three-dimensional picture so you could see what was going on. That'd be very difficult to figure out without one. But this is okay because notice my new order is just, it didn't affect anything. This would have been doing like a double integral and just reversing those outer two limits. So probably didn't really accomplish much on this one, but that's okay. So it's good double integral practice. So that's 9 minus x squared. So if you solve for x in terms of y, you get the square root of 9 minus y. So from left to right, we're going from 0 to the square root of 9 minus y. Lower to upper, we're going from 0 to 9. All right, so to evaluate this upper integral, so the first one, it gets a little messy algebra-wise, but integration-wise, it's not complicated. So we're going 0 to 6 minus x minus y. So dz, so just dz will be z. So it just brings that 6 minus x minus y. Now we have to integrate each of those terms with respect to y. So 6 becomes 6y, x becomes xy, and then y becomes 1/2 y squared, or y squared over 2. So now we have, so we plug in the 9 minus y squared everywhere we have a y. So there, so now we just kind of have to grind out some terms here. So we have to square this binomial and then multiply it by -1/2. Distribute. Be careful with the negatives. That's important, obviously, to get your signs right. So like here in the middle, that does make that a positive x cubed. And then distribute this. And I like to combine any like terms before I integrate. And do I see like terms? Yeah, I see a couple of x squareds. I see a couple of numbers, 54, -81 over 2. And I think that's it. So we basically have gone from 7 terms down to 5. And once you get into this, I mean, you could, at this point, if you get it to here and you want to put it in a numerical feature of a standard graphing calculator. I don't like calculators that can do the symbolic integration. That's why I borrow those for my exams. But when you get to this point, where it's just a single integral, and you can do that and come up with this answer. But you just take the antiderivative, plug in 3, plug in 0, which was 0 is nice because you don't have to really plug in 3. I got 459 over 20. I put the original integral in maple there and got 459 over 20. So I'm thinking I did all right there. That's probably good. Now here's one that I'm you see when it's given like a function like this, it doesn't mean you're going to be integrating anything. It's strictly going to be a setup problem. Yeah, this one I probably should have posted about 10 different pictures of this graph, but I'll do my best to kind of walk you through this one. I don't expect you to have to do 6 different orders on these problems, but it could be kind of fun here. Let's take a look at it. But it can be quite challenging, and I certainly don't want to pick the most challenging thing you can have. So let's see what we have here. So we've got 0 to y as the first integral. And it's going dz, dy, dx. And then y goes from 0 to x squared. And then x goes from 0 to 1. So z equals y, that's a plane. So there it is, kind of angling down. The bottom zeros keep everything in the first octant. Now y equals x squared. Now, if you think, yeah, you're thinking parabola, which you're right, but it's a three-dimensional parabola. So technically, it does, see this red curve here. It does kind of go up and down. Actually, no, this one would never be negative, but it could go down, but it can't go beyond the y-axis over here, negative. It would turn back around out that way, form like that. So, but it could keep going up and down forever. Obviously, I restricted what I put in Maple. I put in the limits. Looks like I kept everything trapped between 0 and 1. And then I put a couple little lines here to indicate. Now it's x is between 0 and 1. Now I kind of smashed this down 2 dimensions on these outer limits to sort of give you a feel for which part of the shading this represents. So just think of that as being a 2-dimension parabola there for a minute. And look at, if you're going from dy dx, you're going from 0 to x squared, like in the yellow here, and then x is going from 0 to 1, left to right. And that represents this inner region here, but now it's lifted up because we're talking volume. But at least on the base, if that's the same base in yellow that we have right here. So this was just to show you that, it's not the part in blue. If this integral would have gone from x squared on bottom to 1 on top, it would have been the blue region. So then it would have been on the other side, and of course I would have rotated this picture around so we could see the other side. But this is the part we have facing us now. So I just to check what I'm doing, obviously this problem didn't really have a calculation, but I just put 1 in there, which 1 means I'm finding the volume of that region. And I put 1 in here of the original problem and got 1 over 10, so that means any order I come up with and I put 1 in there, I need to get 1 over 10. Now 1 over 10 might sound kind of small, but if you think about it, since everything's trapped in a 1 by 1 by 1 cube, if I lifted these boundaries up and drew a cube, that entire cube would only have a volume of 1. So obviously this is just a portion of that cube, so 1/10 is not an unreasonable answer for that by any means, because we're definitely way less than 1. But that's okay, you didn't have to know that. I just thought I'd mention that. So what I think I went ahead and later on I did the other 2 orders, but here I just listed 3 of them. I think I went ahead and did all 6, but I may just stop after these 3 and just leave them in the notes, but just to move on. So dx, dy, dz. All right, so I need x to be some function where it can be in terms of either y or z or both or just numerical. Well, I'll tell you right now, the only time it's ever going to be numerical for the rectangular, remember I told you in double integrals it's only it's only all numbers if you have a rectangle. Well, here it would only be all numbers if you had a rectangular solid, or a cube or some sort of perfectly rectangular solid where none of the variables vary, where it's all just a bunch of straight lines, horizontal and vertical. So obviously this isn't the case here. So the way I would look at this is I'm looking at x in terms of y and z. Now think of it, x is coming out to the right here as I'm pointing. I wonder if I could use a different color pointer here to see if that makes it easier. I don't know. It's coming this way. So you're looking at it from left to right. So if y equals x squared, that means x is the same thing as the square root of y. So I'll go back over here to this 2-dimension one where it's easier to see. So x would go from the square root of y to 1. So that's why I have this down here, square root of y to 1. Now I'm looking for how y is in terms of z. All right, now, so we'll use so the y is going to, the z equals y here, or y equals z, same thing. And so that means as you're moving out on the y value here, going across for the y, it's going to start at z, and it's going to finish right here at 1. It's never going to go beyond 1. There's no other variables that restrict it. It's meeting right here at this line, so it's going from z to 1. And then z has to be numerical, so if y is going to 1 and z equals y, z would have to go to 1. So it would go. So there's our setup right here. Put that in Maple, put 1 in there, and got 1 over 10. So while that doesn't prove I'm right, it's probably a good chance that I am. Now what's the next order? Which obviously I can see it when I see the problem, but dx, dz, dy. Right here. I don't know how looks like I reversed the order there, didn't I? No harm. Actually, maybe I will. I can either reverse the instructions or just reverse the picture here. Trying to make it not too confusing. Yeah, let me do that. I'll just shrink it down. Bring this one down. And we'll bring that other one up, and then we'll do that one now. So, all right. So now we'll have them done in order here. Better stretch that one out so we can see it. So dx, dz, dy. All right, so now I need x in terms of z and y. And let's see what we have here. Yeah, same thing as the last one. If you have x in terms of z and y, or in terms of y and z, it would be the same result here from the square root of y and 1. So now then let's move over. We're working in the dz, dy plane. And now we need z in terms of y. So here's z is the height, so it's that plane in terms of y. So if z equals y like this, you're going from the base, which is 0, to a height of y. So z is going from 0 on the bottom up to y. So that gives you a 0 and y here, and then y would go from 0 to 1 to the edge. And that also produces a 1 over 10. And then this one, dy, dx, dz. So let's take a look at this one. Y is in terms of x and z. Now that makes it kind of interesting now because we can incorporate both of these being variables now because we have, y is in terms of x squared, y is in terms of z. Since y is first, we're going to going out the positive direction for y. We're going from the plane to the curve. So the plane is z, y equals z, and the curve is x squared. So that's why we have z on bottom and x squared on top, because it can be in terms of both of those variables now. We don't have to make anything a constant or solve it in terms of another variable. Now how about x in terms of z? Now this is a little bit tricky because in a way you see that x doesn't really appear to be in terms of z anywhere, does it? But what we can do is we're going from left to right here, or I shouldn't say left to right because it's not left to right. It is when you look at the two dimension. But okay, I'll look at it this way. So if we know that x is the square root of y, correct? If you solve for x there. And we know y equals z, so you can actually substitute that. And if x equals the square root of y, it would also equal the square root of z. So that's how we have square root of z would be the curve, and then coming out to 1, that fixed line right there. So it goes from the square root of z to 1, and of course we have 0 to 1 on the outside. So yes, you see it. In other words, even though x is technically the square root of y, but because of this order of integration, the only variable you could use for x here had to be z, because we always must follow that order. And I kind of wrote it out right here a little bit below so you can see it. Well, look what happened there. That yielded the magical 1/10. Now it looks like I decided to have a little more fun and come up with these other ones. And if you want to look at those, you can. I'll go ahead and skip those and move on, but same kind of idea. All right. So now we're going to use a triple integral to find the volume of the solid y equals x squared bounded by the planes z equals 0, z equals 4, and y equals 9. So I drew it, in y equals x squared, obviously in rectangular form right here. But obviously we have to take the z's into consideration here. But this wouldn't be that bad if you didn't see the three dimensions, because I chose to go dy, dx, dz. Like I told you at the very beginning, sometimes dz goes first, but even without the three-dimensional pictures, z is easy to handle here because it's going from z equals 0 to z equals 4. So it would make sense to put z last if you're picking the order of integration, to put it last, because then it can be represented numerically. And here I have a picture of it, so I just put the plane z equals 4 in there. Did I do any other pictures of it? No. So we're kind of up under there. It's this picture, lifted up with a height of 4, basically. So we have y equals x squared, and we're going from x squared to 9, actually. See, it's bounded by y equals 9. So that parabola, lower is x squared, upper is 9. So we go dy first. X has to be numerical here, even though it's not the farthest out limits. There's no real context between relating x and z together at all here. It wouldn't make any sense to relate x to z. So it's perfectly fine for that to be numerical. You can see the whole thing wasn't numerical because we had that x squared, obviously, because it wasn't a rectangular solid. But there's no relationship, like I said, with x and z here, really. So, all right. So this triple integral right here will do it, and pretty easy to work out the details on this one. So the dy is y 9 minus x squared respect to x. So it'll be 9x minus 1/3 x cubed. Put in 3. Put in negative 3. Be careful here that you don't get 0. This answer is obviously not 0 because we're finding a volume. And we have 18 minus 18, which is 36. 0 to 4 dz, which gives you a z. 0 to 4 basically makes it 36 times 4. So we have a volume of 144. Now suppose, just for the heck of it here, I decided to use my imagination for a minute here and made this a rectangular solid, which, that's not very good. Picture that at negative 3 and 3. Well, okay. Anyway, we would have a base of 6 here. 6 by 9 would be that base. 6 by 9 with a height of 4. So 6 times 9 times 4 would be 54 times 4, which would be 216. So my answer obviously had to be less than 216, but I certainly would not waste time trying to think through that like that on a test for any reason, unless you want to. But yeah, so my answer had to be less than 216 and more than 0, and that doesn't prove 144 is right, but I could have proved it was wrong had I gotten an answer more than 216. All right, setting up a volume. If we're bounded by z equals x, and then y equals x plus 2, y equals x squared, we're in the first octant. I didn't put the three-dimensional picture here. I could have, but in this case, though, if you want to try to start the last example, though, with z being numerical, it made sense for it to go last. But most of the time, if your z is some sort of, in terms of the other variables, oftentimes you're going to want to go first with that. So in the first octant, pretty much bounds everything, including z at 0. So that means dz would go from 0 to x. So it would have a height of z equals x. And it would actually be not the same plane as this one we did back up here. See, z equals y, it would actually be, from this view, it would be angled up coming toward us, z equals x, sort of a flat angled plane. So that means the height would be x. That makes it much easier. And then you can focus then on 2 dimensions like you would for a double integral, and that makes it a lot easier. Then you can just work with this picture in the red. So you know you're going from the curves on the bottom, the lines on the top. We go from x squared to x plus 2, and then dx, so we're going horizontally from 0 to 2, and then that'll calculate that volume. Pretty easy integral. That puts you in x here. Antiderivative of dz would be z. But okay, now I got it. Okay, I skipped a step here. I thought I was confused, but the antiderivative of dz would be z, which would bring an x in. Then you go x minus 0, so there's where that x is from. Now integrate respect to y, so there's no y, so it's just xy. I guess you can say there's a dy, but bring in the x plus 2, bring in the x, so now we have x times x plus 2 minus x squared. So just, there's nothing to combine there, but distribute these terms. You end up with this integral. I didn't even bother to finish this one. It's not too difficult. But like I said, I did the f and it, which this is an older operating system for the calculator. Now when you do under the math f and it on the TIs, it shows you an integral now instead of the old school way of doing the f and it here. Actually gives you an integral symbol. Well, no, okay, actually I did graph this thing. Yeah, so there's, well, I can rotate these in Maple, but not once I've pasted them here. So you see, it's that curve, there's that curve base. So what we just found in the volume was that curve base, and then just there's the z equals x plane angled right there. So it's that curve base, and then it's just imagine it being lifted up from the bottom, and then it's bounded by that plane right there. So that's where it'll stop. So my sketch isn't the greatest there. I realize that, but that's, so I didn't realize I'd graph this, but okay. So that's kind of what we were looking at. So you didn't really need to see this picture. I think the one we did earlier, though, I think the picture was definitely needed, and I would certainly take that into consideration. This one, though, was easy enough to set up without it. And this one isn't bad either as far as the setting it up. 9 minus x, z equals 9 minus x squared, and then y equals negative x plus 2. And so I would go with that. You don't really need the picture because you can just go 0 to 9 minus x squared and start with dz, and then just focus on that triangular base, which you might want to see it in this form. I think I might go back before I post these notes along with this video and use the graphing calculator to make that look a little nicer, but it doesn't affect anything. Let's see. So yeah, so you have y equals negative x plus 2. And so you would be going from, if you go dy dx, of course, which you had certainly had free choice of what you wanted to do here. So you go 0 to negative x plus 2, or 2 minus x, same thing. And then x would go from 0 to 2 going across. So not too bad. You just work out the mechanics. This one, so it's 50 over 3. Yeah, once again, okay, at least I did do the integration, but I just didn't plug the number in. Showed it in Maple, got 50 over 3, so there's a good chance that I'm right. It would be hard to luck into that answer. Now I decided, just for exploration, let's look at if this was a rearranging type of problem, which this kind of problem, if I wanted you to do something this complicated, I would absolutely have to give you that three-dimensional picture. But just to get the volume by choice of any order, dz, dy, dx, as you can see, it was not, you didn't really have to have that picture, because just go from 0 to whatever the z function is. But to go different orders, it gets a little scary here. Now, especially down here, I'm really not interested in doing this to you. I did promise that most likely on the test I'll have the sum of two double integrals. But the last three get really scary because you got to do two sets of triple integrals. I'm not that brutal, so, but you know, you might enjoy taking a look at those. But let's take a look at these real quick. So if we go, let's say dy dz dx. So I started with y first, and you can kind of look at this picture right here. I'll work with that, so that kind of applies to everything. So y, right, and look at it from this way, is going from here to the plane, which is 2 minus x, which obviously, if you're on the xy plane, it's a line, but here it's a plane. 0 to 2 minus x, so there's that one. And z would go from, see, z can be in terms of x. And now don't worry about that split, that red plane right there. I'll explain that in just a second. That has to do with these more complicated issues. But as far as, or actually I could probably go back to this other picture, but it's not conveniently located for me. But anyway, it would go 0 to the plane, the height. So it's 0 to 9 minus x squared. And then x would have to go from 0 to 2, like it does right there, right here. So you can see that produced 50 over 3. And then this one, dz dx dy. So that's not too bad. That one's actually really easy because it's just taking the basically problem we did up here. And if you took this equation y equals negative x plus 2 and solved it for x, you would get x equals 2 minus y. So that one's really easy. So it goes, well, assuming you got the first one right, it's easy. So you go from 0 to 9 minus x squared. So now it's going from 0 to 2 minus x. And then y goes from 0 to 2. That yields 50 over 3, which is terrific. But where it's on what, well, not going into too much detail, what makes this one have to be separated at z equals 5, that's where, because you're going to have some of these other issues, you're going to have to split this as two sets of double integrals, one on the bottom and one on the top, because if you're going in the x direction, you've got two different regions. You're either going to the plane y equals 2 minus x, or you're going to the curve. So depending upon the order of integration, I guess I could take a look at one of these real quick and not do all of them, but this one, y, it's mainly because of that x more than anything else. You have to split it because the x is the problem. But if you look at this bottom one, 0, plane z equals 5, dy would go from y to 2 minus x, right there, here. No problem. And then x goes from 0 to 2, and then z goes from z, because it's constant, and then the z would be constant because we added a flat plane in there, makes that 0 to 5. It's all because y going this direction in terms of x has two different, or x, yeah, basically two different representations of x. Now you come over here, the upper part of this, you see the difference. The z limits now just becomes 5 to 9 right there. Remember, the outer has to stay numerical. And we're still going from 0 to 2 minus x on the base here. But notice what the x is doing. X is now going from the axis to the curve. See, below it was going to that plane 2 minus x. But now x is going to the curve. Z equals 9 minus x squared. So if you solve for x in terms of z, you'll get x squared equals 9 minus z. So x then would equal the positive square root of 9 minus z. So it goes from 0 to the curve. Now notice those two added together, look at that, gives you your 50 over 3. So this one does take some, fancy thinking on some of these. And one of them I had to sort of change the, okay, you can read that if you want to, but there's about zero chance I would have to come up with this design that I did by reversing the axis to make that last one work. And I think you can do that, and it worked, but I don't know. But anyway, yeah, if you want to read that, you can. If not, do not worry about it. I can't imagine anything being that complicated you'll ever need to do, and certainly nothing I require. So, all right, so that is the end.